Hello folks, in this video tutorial I'm planning to show you how to apply a non-uniform pressure distribution in the 3D Experiences FEA solver, which is actually the Abacus program. Now this comes under the using map data strategy, and when you look at the YouTube you see a lot of references for the Abacus CAE where they actually do something like that. Unfortunately, those things are not directly applicable to the 3D Experience platform, and therefore I decided to go through a very simple rudimentary problem, okay, where the pressure distribution is applied by the user and it's non-uniform. Incidentally, I do have a video tutorial doing more or less the same thing in the CATIA program. CATIA's native FEA solver is actually Elfini program, whereas in the 3D experience, it is the Abacus. Now, let's take a case of a Pullman aircraft. There's a fuselage and there's a Pullman wing. And suppose you want to find the response of the wing under some kind of a loading which comes from aerodynamic forces. Now, obviously, that's not uniform. So presumably, one does a CFD calculation if needed and get the pressure distribution on the wing. I'll just worry about the top portion, and which is incidentally nonlinear, and then solve it. Okay. Now, what happens is that the 3D Experience or / Abacus takes this data, which is either coming from an external source, such as an Excel spreadsheet or text file, or manually input it, as I will do that, and does some kind of interpolation based on the coordinates of these points and the values that are described, and then use that in order to estimate the pressure distribution on the geometry. Okay. Unfortunately, documentation in the Abacus / 3D experience for this particular issue, the interpolation strategy and some of the details are not very, or is very dense, and therefore I'm not looking at the most general situation. I will look at a very specific, simple example. Incidentally, I'm assuming that the material is linear because that has nothing to do with the way I describe this information, provide you with this information. The dimensions are given of the box are given by that. This is a poor man's aircraft. It's only 100 millimeter long, 100 millimeter long wing. And I'll do a sweep meshing, as you see here, with 2 layers. Now, what I will do first is to show you how do you input this information in the 3D experience. And then I will come across this screen later on. And then I make some changes which are in the following slides. Let's not worry about that. We go up to 3D experience. Let me start with the part file. Make a block. As you see on this vertical axis, I will make a block which is 100 millimeters by 10 millimeters wide. So it's like that. So this height is this is 100 millimeters, and this edge is 10 millimeters exit, and then pad it by 40 millimeters to get that poor man's wing. Okay. Good. Let me apply my material properties. I'll go to Tools, create a material. Just call it a poor man wing. Poor man wing. And say OK. I think this was misspelled. Should be man's. Okay, manned. Okay, that's no problem. So apply. on this. Close that, green check mark, and now we put our values here, which is just Young's modulus and Poisson ratio. This is made out of steel. Made out of steel. Abacus multiphysics, elasticity, 200 gigapascal, GPa, and Poisson ratio of 0.3. And that takes care of it. Okay, so now we're going to go do meshing of this. So we go to 3D. 3D. These are my favorite applications, and I want to do the structural model creation, which allows me to mesh empty FEM. And for meshing, I will do sweep meshing right there, sweep 3D mesh right there. So it sweeps it through this direction, 2 layers and 10 millimeters each. Because if you look at the dimensions that I have here, these are roughly 10 millimeters. Actually, I said that 10 millimeters right there. Okay, so let's go ahead and mesh it. Nothing fancy. We say, okay, let's apply properties to it. So properties, solid on that part. The poor man's wing is selected. Material property selected, and that takes care of the mesh. We now go to the structural scenario creation. After all, I want to describe how to apply this, but I'm not interested whether it's implicit or explicit. I am using implicit static problem. So structural, and the model is the one that we just created. There we are. There's no procedure here, so we go and do a linear static step. Now, if I do linear static step, I'm going to uncheck the geometric nonlinearity because I just want to do this thing one step. The alternative, if you want to do that, the alternative is to use the static perturbation. Static perturbation really means linear static analysis with no geometric nonlinearities. That's pretty much it. So I'll do this. Okay, so we say okay. Good. So we now go and let's go and clamp this side. So we go to boundary conditions. Under clamp, we select that entire face, or you can select the face, say no translation X, Y, Z, etc. That's the same thing. All right. Okay. Now we apply the pressure. So what do we do here? This is where essentially the content of today's video is going to show up. So we go to loads. Here is the pressure. You click on it. If you have a uniform pressure, just put the numbers here and you're all done. Well, first of all, the support is that face, as you can see. If you have a uniform pressure, just put the number here. But we don't have a uniform pressure. So we go here, expand this thing. You want to do a mapped spatial data. Mapped spatial data. You click on it. Okay. So right now, I have right now I have this, so I click on the table. I click on the table, you click on the table, this thing pops up. And what you see here is actually this screen right there. If you want to import your data from an external source, you do right click, import. I don't want to do that. I just want to put those numbers manually myself in this table. Let's look at a few things here. By the way, you can do it with a table, or you can do it with a reference document on 3D Experience, as I said, or just import. But first of all, there is a number here. There's a box here which says pressure outside the mapped region. So when I give it my X, Y, Z's, it will internally generate a domain here which will do interpolation to find pressure on the elements within that map domain. Anything that is not in the map domain is going to be assigned the value that you put in here. For now, I'm just going to put 0, no problem. And these are the values, these are the coordinates that I want to assign with those pressure values, and outside is 0. Okay, so basically 5 points along that line, I'm going to input in that table. Now, if you have other units, no problem. You can just, I mean, mine is millimeters, but if you had other default units, that's the way it's going to appear. Okay, so if it was meter, you just have to put meters in here. So these points on the top, they are 10 millimeter in X. Let's see now, 0 in Y, and 10 millimeter in Z, which means that top top surface. And the value at that point is I have 30. Then I go to 20 millimeters. Notice that these are in, sorry, 10 millimeter. These are entirely up to you. These are your coordinates, the coordinates of the points where pressure is provided from whatever source. So 10, and Z is 10, and the value of the pressure is 20. It just happens that in this particular problem, they are the coordinates of these corner points, but they don't have to be. 10, whatever is in your Excel spreadsheet, 20 millimeters, height of 10 on the top face, and the value is 15. Two more. This one is 10, 30, 10, and 10. And for the last one, I put down 10. This is going to be 40. This is going to be 10. And I just make it 5. Okay. Now, so what I did, I input these numbers, and you know what this thing means. Anything outside of the domain that is mapped by the program is going to be assigned a value 0. Okay. Now, notice that there is this tab here which says pull down menu, which says global or local access system. See that? We'll go back here. Now, these are global coordinates. That's the way I want it. But if it's convenient, you can actually create a local and put the coordinates. Obviously, I don't have one, but you can go and create one. You can go and create it. I don't want to do that. And then put the values of X, Y, Z based on the local coordinate system. Now, remember, these things usually come from an external source, a CFD calculation perhaps. And there, of course, you have X, Y, Z, whatever it happens to be. Now, there is also this thing called plot data. First of all, before I go any further, notice that you can go to any one of these rows, for example, this item number 1, and this point lighted up right there. We can see that, this point right there. Go to the next one, this lighted up. This next one, etc. You can see where your pressures are actually applied. Or you can just say plot the data. If you say plot data, move this one aside. So what you get is color coding for, let me move this thing out of the way. It's just a color coding for these points. See, red, 30, green, whatever, 20, etc. It is not very, this is not very convenient, but that's what these colors are. I looked at my screen and I figured that, oh, it matches what I put in there. Okay, so let's go back here. One last thing, you can specify some tolerances because it could be that you actually create or you actually had a point XYZ which was not on that surface. Then what it does is just excludes that based on these tolerances. As I said, if one wants to use this thing in a serious way for some calculation, then you have to consult the Uh, the detailed uh, abacus manual, perhaps the theoretical manual, and because in what's available to user, that stuff is not there. Okay. Um, anyway, so you may have to contact the people at the SAW or Simulia and get some information because that cannot be extracted from the documentation. Let me go ahead and I'll put a few pages of documentation for you at the very end in case you want to look at it later on. Okay, so that's good. We are good here. And we say, okay. You can always look at it again. Oh, here, right there. You can make changes, etc. So this is fine. It was global. You say okay, and you say okay, and we're going to run it. So let's go ahead and simulate. Let's do a model scenario check. This is one-step linear analysis. This is a simulation check. I don't anticipate any problems. It is a complete mystery on how this algorithm is implemented there. Some codes, for example, CATIA, they tell you that the Alfini program in CATIA, they tell you that they project things on the surface and then they put the information on the centroid of the element, etc. But it's totally in the dark on how this is done. For simple problems such as the one that I'm doing, it's obvious there's no issue. But for more meaningless usage, you really have to know the details. So simulate, and this is going to bend downward, and the pattern is not symmetric because notice that I did not take my x to be exactly halfway between that x line. Those pressures had x of 10, which means not symmetric. If I had used x of 20, it would have been symmetric uh, on both sides. Okay. Once you get the okay, the box and say okay, this will run in no time, pretty much. So it's one-step linear analysis. Or I rarely have the reason to do something like that. But the reason I did this video is because one of the subscribers contacted me and said, how do you do non-uniform pressure? Then I decided to go and find out. And I realized that it's not hard, except that it's not properly explained. So, okay, so let me close that. There we are. Not symmetric. This is the one meso stress, by the way. Okay, if you want, you can plot other things such as the pressure and things like that, but that's okay. This is one meso stress. Now, what I want to do is I want to go here and say, okay, what if I wanted to specify the pressure only at these points, okay? And and outside of this region, whatever it is, the pressure is minus 10 MPa. Okay, so at these 3 points in space, this is what value of pressure is, perhaps coming from a CFD code, and then outside, anywhere else, is going to be minus 10 MPa. Okay, all right, so what I want to do is I want to keep 20, 0, 30, and 40. I go here. Let me go back to my table, which was here, pressure, right there. Click on this. Okay, you go to the table, keep 0, 20, and what was that? 0, 20, and uh, wait a minute. Points with y equal to 0, 30, and 40. 0, 30, and 40. So I want to delete this row. Put the cursor there. Say delete this row. I want to delete 20. Delete this row. So for y, it's 0, 30, and 40. And anywhere outside, this pressure is no longer 0. It's minus 10 MPa, which means upward. Now, if you want to get some idea about the points, you can click on this plot data, and it shows you the colors. Here is a red, okay? Let me say okay, and then get into it again, because plot data. Let me try it again. Say okay. Get back into it. I noticed that it's very finicky about this. Table, plot data, right there. Now you can see it better. See right there. The data is on this side, and the colors, there's a red here, and then you go here, there is a green, and there is a blue. You can change the size of these things, but it's not worth the effort. I want to show you what I'm doing here. So where is this? Right. So I just selected this, kept this, and everywhere else is minus 10. So if I go here and now run it, say okay, and then run it, I don't have to do the model check, scenario check, it's going to work fine. This actually is going to go up because there is more force pushing it upward. There's more area where minus 10 is applied, so it makes this thing go up incidentally. These arrows that you see here, the pink arrows mean nothing. It's just a icon for pressure. And if you hide it, unfortunately, you can't see those little dots if you ever need it. It's not Pressure is not uniform. You can see that. All right, so let's run it. Okay, so we close this, and you can see that it did go up. Let me do one more thing, and I want to so that actually see the pressure on the top face. So what I'm going to do is I'm going to go to results. Okay. What about okay? I'm going to add another display group here. So I put my cursor on these on the sketch, on the figure, on the illustration on the screen. Click on it. Okay, try it again. Click on it. Display group. I want to create a new group called group number 2. Okay, so if I let me see. So fine. Let me go there. So what I want to do is I want to create surfaces. So let's see now. Entities, pressure, right? Pressure, for example. You say so what I'm going to do, I'm going to say pressure and then replace. There's replace. There we are. Okay. And let me close this thing for a second. So apply. There we are. The second one is the other. One of them is bending. You have to look at these numbers to find out what is what, because all it gives you the components. Okay. So this is S22, so it must be SYY, and S33 must be the vertical pressure. Yeah, that makes sense. Okay. That makes sense. Okay. So as to see, we have Y, X, Z. Okay, before I stop this video, I'm going to go to the documentations from the 3D Experience / Abacus. And I'm just going to put it on the screen for maybe 2-3 seconds. If you ever want, you can stop it and read it. I try to put circles around things which are important. This is in case you want to export data or actually import data. This is the format that you have to do it. Exactly the way we inputted it. Here's an Excel spreadsheet. You can see that for X, Y, Z, and this is thickness is not pressure, but things can be imported for anything. State data, map data is not only pressure; it's for other stuff too. It's very dense, and it gives you a few lines about the search method and tolerances, but you really need beyond these slides in order to find out what is going on. This is the second last. And the last one. Okay, folks, hope this was useful.